Hello everybody, I'm Benjamin Lang from the Norwegian Polar Institute, and I'm going to be presenting some of the first results from the Underwater Hyperspectral Imager, which was integrated and deployed from the ROV during leg 4 of MOSAiC. And we're going to be looking at different ice types, sea ice ridges, and level first year ice. So typically over the past 50 years, for biogeochemical sea ice properties, we would have to take ice cores, and this is a lot of work, and you would have to take several of them to get any good representation of what's happening within and under the ice, or at the bottom of the ice. And over the past 15 or so years, there has been development in remotely estimating sea ice algae biomass and other bio-optical and biophysical properties using hyperspectral radiometers. This has led to some really good studies on the distribution of sea ice algae, and you can do this by looking at the spectral signature of the light transmitting through the ice. And this has been developed also in remote sensing, satellite remote sensing, and airborne remote sensing, and applied similar methods to these approaches. And now recent developments in underwater hyperspectral imaging have allowed us to get surveys of the bottom of the ice at microscale spatial resolution. And this is really important to get a better understanding of how sea ice algae is varying over space and time. And it's a non-destructive method so that you can do this and not have to take several ice cores over time and not be able to measure the same location. So in this study, we were able to survey the same location several times over a month period. And in the future, we'll be able to get a very good idea of how sea ice algae are responding to the changing environment. And then this will lead to better understanding and representation in sea ice models. So to give you an idea of what the data looks like here, this is a snapshot of, or a subset of one of the surveys we did. And as you can see, you have very many grid cells. In each grid cell, there's a spectrum. And in the left figure here, you see the integrated PAR. So this is the integrated value of the light in each pixel. And this is a very important and really cool figure in itself because it gives you very small scale, about centimeter resolution information about the optical properties of the sea ice. And for the Arctic, this is one of the first surveys that has been done for Arctic sea ice. And then to give you an idea of the four-dimensional data set, you have the spatial dimensions, the pixels on the Y and the X axis, and then you have the Z value, which is wavelength, and then for each of those you have a magnitude of the light in each of those. So you get a lot of data, and this is one of the first issues I encountered with processing the data, is that you go out and survey for an hour and you get gigabytes, hundreds of gigabytes of data, and then to process this, it's really challenging if you don't have a supercomputer. And so we just started to do the subsets of the data, and we were able to come up with some interesting results. But just to give you an idea, and this is just randomly sampled a spectra from the different surveys to give you an idea of what the spectral variability looks like within the surveys. So during leg 4 of MOSAiC, we arrived at the flow at the beginning of June, and we set up all of our different locations. We found a nice ROV station near the ship, and this was important because you wanted to get there relatively quick and be able to do surveys and then get back to the ship and troubleshoot and bring large equipment small distances a lot easier. So this is a bottom ice topography map that came from the multi-beam sonar that was integrated into the ROV. And as you can see on the right of the image, you have Ridge. This was the ridge that we sampled for regularly over the entire leg of MOSAiC. And we surveyed with the UHI a couple subsets of this larger area, because it's quite difficult to maintain steady survey lines. So you can see we have one area which covered the ridge and the flank of the ridge, and then we had another area of level ice. Now here is one of the surveys we did on July 7th, just as an example. So on the right you have the transmitted radiance As you can see, it's relatively low values, and but the other thing that's really interesting is you get really small scale, micro scale spatial variability of this transmitted radiance, and then this will be important to relate to the geometry of the underice blocks and different properties from the surface, such as the snow, and also surface geometry of the blocks. And then I did a simple application of an NDI to the spectral measurements, and this is the normalized difference index. It's a proxy for sea ice algae. This was one of the algorithms that or the wavelength combinations I took from Monday et al. 2007, and just applied it to the UHI survey to get an idea of how it's working, if we see anything. And it looks relatively good on this one, and also for the level ice, you can see much brighter light. But when you look at the NDI, you get quite contrasting results from the two different ice types, the ridge and the level ice. And my first impression of this is that it's likely because of the magnitude of light. So this is not really a great start to the analysis, because this is the one thing you do not want to have when you look at the algae signature from the spectra. Is you do not want the signature to be coming from the magnitude of the light. You want it to be coming from the shape of the spectra, so the wavelength combinations or the specific shape of the spectra. So at first it looked promising, but now I need to look into this a bit more and maybe try different NDI combinations. But we have other algorithms we were looking at, and I'll go in after. Yeah, so we have just the regular RGB combination to get a visible impression of what's happening at the ice, and you can see a lot of melazeo strands in forests. So this is what I used in some of the other algorithms to develop classification. And then we used a more typical remote sensing algorithm, the normalized difference vegetation index. So this is using the near infrared and the red, and then the NDI, and then this is the integrated radiance. And having all four of these beside each other, you can get an idea of the magnitude of the light, where the algae are in big lumps, and how these two algorithms are capturing this variability. So as you can see, as I zoom into this area, the two algorithms are capturing these algae patches quite nicely. And we have to look into this a bit more, because you can see also that maybe the NDI is capturing some of the shading or the low magnitude light. And this is something we want to try to avoid. So we're going to need to look into this a little bit more. So another algorithm I started to look into was the machine learning based UHI analysis, and this has been developed extensively within the remote sensing, the airborne and satellite remote sensing field. And now I'm going to be looking into this in more detail and trying several algorithms. The first one I tried was the support vector machine algorithm, and this is essentially supervised classification. If you're familiar with remote sensing, then you'll maybe know this. And yeah, then we will go into assessing the model, and then this will create a predictive model that we can apply to the rest of the UHI dataset. So the first step was to do a principal component analysis on the data, and what this does is it looks at the variation within different parts of the spectrum. So as going from band 1, which would be PC1 through PC8, and here they're called bands, you progressively explain less and less of the data set. So we use this, and we combine this with the supervised classification part. And this is where it was quite manual and tedious, and I looked at the RGB images to find areas where there's algae, like this, and I would classify the areas of this algae or non-algae, which was quite straightforward. You can see these really large melazeo strands. And then so I classified those. And then what the model or the algorithm does is it does a test on this. So it takes the different PCA bands, and it develops a predictive model for algae and non-algae based on the locations that I have selected. And then it does a test, cross-validation test, where it subsets the data and it develops an algorithm, a predictive model based on a part of the data and applies it to the rest of the data, and it iteratively does this thousands of times and comes up with the best model. And what you can see from this is that from these nearly 2,000 pixels, only 16 occasions has the pixel been assigned as no algae when it was actually algae. So this is quite a good result for the assessment. It's over 99%. So that's a good indication. And now I combine this PCA, the ground truth data set, I do the assessment, and then we apply this predictive model to the data set. And we come up with this classification where it's no algae or it's algae. Now, if we take this and we compare it to the other algorithms, you can see that perhaps this algae may be overestimating, or maybe there is algae there, but it's just not visible from the RGB image. But nevertheless, if we take a closer look, you can see that perhaps it is overestimating the areas of algae in comparison to the other methods. So again, this is my first impression, is that this is likely a result of the different light regimes that each habitat is having. So we have a level ice habitat that has quite relatively uniform light field, and then we have a CS ridge, which has a quite variable light field where you have almost no light, and then you have high light. And you need to really capture all of these different locations within your algorithm in order for it to have really good predictive performance. So I have to do a little bit more analysis, comparison, and assessment of these models, and develop some, or look at different machine learning algorithms as well. There's many others, and I'm going to be diving into that a little bit more. So I've shown you that a nice groundbreaking approach for microscale to flow scale, spatial variability of sea ice algae, and the biophysical properties. This has already been developed for Antarctica using under ice sledge, and there are 2 studies showing their results, and they came up with some really unique groundbreaking results for Antarctic sea ice. And here we're going to be developing upon their results and having the first ever results from Arctic sea ice, and first results for sea ice surveys with the UHI mounted on an ROV. So this is really important for the spatial temporal analysis of sea ice algae and biophysical properties. And then also we have different habitats that we're comparing. So as the Arctic sea ice is becoming more mobile and more dynamic, ridges are expected to become more prevalent. So this study will help us understand what the differences are, how they change over space and time, and this can give us a better indication of how the Arctic will change and how the different sea ice algae habitats will change in the future. Thank you.